Oh, can you hear me? Okay.
Yes.
Yeah. All right. Oh, I'm really sorry. Okay. Um, yeah, so today I'll be presenting Alex and I's work on Education Warm Start for Petrick. We really enjoyed the challenge, so thanks, Chris and the team for setting this up. And I'll quickly, yeah, start. Oops. So as was stated before, so the sort of objective, the goal of this challenge was to get some converged solution xref. We have a known objective function, and we want to get to this xref as quick as possible. And the idea, what we came to for approaching this, is that we wanted to have some sort of deep learning. We want to try kill it with data, but we'll show that that was a bit of a mistake. But so we wanted to combine deep learning as a warm start for then an optimization algorithm. So how can deep learning help with optimizing this objective function? So there's a nice paper where they're talking about learning to optimize, where you can say that your next iterate xk plus one is your previous iterate and some gradient of your objective function with some neural network on it. So that would be like a full gradient update just based on the output of a neural network. You can also try and learn a preconditioner. So you could write it out like you have your previous iterate, your xk, and then you have some step size, and then you have a neural network, which just is a diagonal preconditioner in this case. And the convergence of this sort of formulation is only is you have to have very strong constraints. And what we found is that for the size of the volumes, for the number of volumes, for the variety between the volumes of the training set, what we're given for the challenge, we weren't able to achieve any speed up, to be honest. So we kind of abandoned that and went with this warm start approach instead. So the idea here is that we can hopefully get a good initializer or warm start image for our classical iterative solver or this optimization method, which comes afterwards. Um, and how we approach this is we had took a neural network, and we trained this in a supervised manner. So with part of the challenge, we were given like an approximate OCM image, and then also we were given the reference images, which we were trying to approach. And we just treated this as supervised training. And additionally, we found that constraining the network further helped. So we made our network one homogeneous by removing all the biases and just having ReLU activations. And this meant that we could generalize a bit easier to different intensities. Um, yeah, so we have a network, we have an OC image, we have our network, we apply our network, we get a warm start image now. And now we need to talk about the optimization algorithm, which was really the sort of meat and potatoes of what got us to our converged solution, or what tried to get us to the converged solution. Uh, so here, as Georg talked about, is that we can sort of break down this first order algorithm into some sort of your previous update or some initialization, which we talked about. We're going to have a warm start now. And now we're going to have some step size rule, we're going to have some preconditioner, and then we're going to have some gradient approximations, and potentially also have some acceleration and momentum terms. For our first algorithm, so Georg mentioned in Robbie's paper, he tested Saga, and we implemented Saga as well. Instead of SVRG, it's just a choice we made. And we also added some momentum. So firstly, I should talk about the step size rule. So we chose, instead of the BV step size rule, there was a paper that came out quite recently, which looked at step size rule called distance over the weighted gradient, which I don't think we'll have time to go through, but we use this as our step size rule. As our preconditioner in this algorithm, we use just a EM preconditioner. So I guess, I hope I'm right, that's what Robbie's paper did as well. And then we also used as a gradient estimator. So this is your kth objective. So this is a subset gradient, and this is your subset gradient at your anchor image, which Saga uses to help convergence. And we also added a Katusha-like momentum term as well, which was based off, this is an anchoring term, based on a full gradient update or just after a full gradient update. And so it's Saga, which is meant to be stochastic, but we decided abandon stochasticity and focus on just having a set of subsets with a given order, which we chose staggered, which I think everyone probably did and might have been one of the first things everyone changed. And then we accessed them in this specific order, which is the Herman-Mayer order. For algorithm 2, we chose to implement SGD with the step size. And instead of just the EM preconditioner, we chose adaptive preconditioner similar to what similar, not similar, but like sort of like what Georg mentioned. So in the case when Poisson likelihood dominated, we found that it was okay to just use the EM preconditioner. But if your RDP, so that regularizer component of your objective function is strong, then you also have some diagonal diagonal of your Hessian of your RDP as well. And we used the row sum approximation of your likelihood, or some approximation of the Hessian of your likelihood. Sorry, that's a word salad. As this likelihood term for your preconditioner if the RDP was strong. We just found that worked. And then our SGD gradient estimator is that we just cycle through our subsets. And our final algorithm, we used just full gradient descent. And our reasoning for this, I can talk about briefly if it's of interest, but in this case, we just use a BB long step size in this case for how we choose our step size. And then we have, again, this adaptive preconditioner. So if a Poisson likelihood dominates in some sense, then we use our EM preconditioner. And if our RDP is strong, then we use this other preconditioner, which has this diagonal Hessian of your relative difference prior. I should note that this is updated every 2 or 3 iterates, but this kappa squared is exactly that used for the RDP kappa. It's the same kappa, so it's based on the OCM image. And this is just full gradient descent. So this was our stable method. Yeah. So, and we also had lots of different ideas we tested. So in the sort of deep learning ideas, instead of just having XK, which is the previous iterate, and having some supervised learning, we also looked at changing the training loss. So because we actually have the objective function we're trying to optimize, we can put this in place of a supervised training loss and have an unsupervised training loss, which is just trying to optimize the exact objective function which we're trying to optimize. So we tried that, but it just didn't work, especially if the fact that all the metrics which we evaluated the thing at the end were based on an image. It makes sense to use a supervised training loss. We also looked at network unrolling. We also looked at changing the input. So instead of just XK, we looked at adding the gradient of your objective function as an input as well. And then we also tried different optimization methods. So sort of these, you can think of it kind of like an adaptive preconditioner. So like the sort of usual suspect is added, which pops up a lot in deep learning literature. We kind of were curious at how that would work for pet reconstruction. Didn't work too well. We also looked at the row sum of the RDP row sum of the RDP Hessian, I should say, rather than the diagonal. And you can do that by using PyTorch. And Georg mentioned that you can write out the Hessian of RDP, the diagonal of the Hessian, but then there's an epsilon parameter, which isn't in the original paper on RDP, which you then, we used Wolfram Mathematica to figure that out. We didn't. We also looked at some other things. So if you just accumulate your gradients every few steps, then you asymptotically converge as well. And we also looked at other momentum terms and heuristic choices for step size and initial step size. There's a lot of sort of tuning. It turned into quite the tuning nightmare, but that gave us an outline of what we did for this challenge. Thanks.
Thanks, Imraj. Any questions for Team EWS? Georg has one.
Thanks, Imraj. You mentioned on your slides that you had these rules depending on whether the likelihood was strong or the prior was strong. So how do you decide whether, one or the other is strong? Is that based on curvature, or how do you do that?
We had something extremely. So we looked at the norm of the RDP gradient versus the like the ratio of the RDP gradient at the OSE image divided by your full gradient, the norm of your full gradient. And if that was above some heuristic, which we chose as 0.5, then we didn't. We found like a really big expense was recomputing the diagonal of your RDP Hessian. So to avoid that, that's what we have this heuristic to begin with. Yeah. So it's just a heuristic. Yeah.
Okay, thanks.
Okay, I see no more questions. So thanks, Imraj and Alex,